Picture this: a world where the ground beneath your feet is alive, shifting in a slow, relentless dance over millions of years, where continents aren't fixed landmarks but colossal wanderers, crashing together with unimaginable force, reshaping the very face of our planet. This isn't science fiction, it's the epic story of Earth itself, a tale written in rock, fossil, and the scars of ancient collisions. Today, we're peeling back the layers of time to uncover the hidden drama of continental drift, the monumental clashes that turned a fractured world into the one we recognize today. Think about the map. You know the familiar shapes of Africa, South America, North America. Now erase them. Rewind the clock 250 million years, and you'd find yourself standing on a single, gargantuan landmass, Pangea, a supercontinent that held all of Earth's dry land in its grasp. But this wasn't the end of the story. It was just the beginning. Beneath the surface, titanic forces were stirring, pulling Pangea apart, sending continents adrift like ships on a molten sea. And when they collided, oh, the chaos that followed. Mountains erupted from flat plains, oceans vanished into the abyss, and life itself was forced to adapt or perish. What if I told you that the Himalayas, the tallest peaks on Earth, are the result of a slow-motion car crash between India and Asia? Or that the Atlantic Ocean was once just a crack in the Earth's crust, a tiny rift that grew into a vast watery divide? These aren't just geological trivia, they're clues to a planet in constant flux, a world where the ground is never as solid as it seems. So buckle up, we're about to journey deep into Earth's turbulent past, where continents clashed like titans, and the very stage of life was rewritten. By the time we're done, you'll never look at a map the same way again. Long before Pangea dominated the planet, even earlier supercontinents rose and fell in Earth's relentless geological waltz. Imagine a time so distant that the continents we recognize today were just fragments of something far grander, colossal landmasses like Rodinia, which sprawled across the planet over 1 billion years ago. This wasn't just a single event but part of an ancient rhythm, a cycle where continents merged, clung together for eons, then shattered like glass under pressure. The evidence of these lost worlds lies hidden in plain sight. Take two rocks, one from Australia, another from North America, and place them side by side. Their mineral makeup, their age, even the magnetic signatures locked inside them match perfectly, as if torn from the same fabric. That's no coincidence. It's a fingerprint left behind by Rodinia, proof that these now distant lands were once neighbors in a forgotten supercontinent. But how does something as vast as a continent break apart? Picture a pot of soup simmering on a stove. The heat beneath causes the liquid to churn, bubbles rising and pulling the surface apart. Earth's mantle works the same way. Molten rock swirls beneath the crust, generating enough force to rip landmasses in two. When Rodinia fractured, it didn't just split cleanly. It sent fragments drifting in all directions, setting the stage for new collisions millions of years later. And this wasn't a one-time spectacle. Before Rodinia, there was Columbia, another supercontinent that came together around 1.6 billion years ago. Its existence is pieced together through scattered clues, mountain belts that abruptly end at one coastline only to reappear across an ocean, or fossils of identical prehistoric algae found in rocks now separated by thousands of miles. These aren't just geological quirks, they're chapters in Earth's autobiography waiting to be read. The most fascinating part, this cycle never truly ends. Even now, the continents are on the move. Africa is creeping north, destined to crush into Europe and resurrect a mountain range taller than the Himalayas. The Atlantic Ocean widens by an inch every year, while the Pacific slowly closes. The same forces that built and destroyed Rodinia and Pangea are still at work, reshaping our world in slow motion. One day, far in the future, Earth's landmasses will collide once more, forming a new supercontinent, and the dance will begin again. Pangea wasn't just another supercontinent, it was Earth's final, breathtaking act of unity before the grand fragmentation that shaped our modern world. Imagine standing on its vast, uninterrupted plains, where the future locations of New York and Morocco would have been neighbors, separated only by rolling landscapes instead of an ocean. This wasn't just a landmass, it was a colossal puzzle where every piece fit together, from the jagged edges of South America and Africa to the sprawling connection between North America and Europe. The birth of Pangea was anything but peaceful. Continents slammed together with such force that the planet's crust buckled, giving rise to mountain ranges that dwarfed anything we see today. The Appalachians, now worn down by millions of years of erosion, once rivaled the Himalayas in height, a testament to the sheer power of India-sized landmasses colliding. Meanwhile, the Ural Mountains, which today divide Europe and Asia, were forged in a similar fiery embrace between Siberia and the ancient continent of Baltica. These peaks weren't just geological features, they were scars left behind by Earth's restless tectonic ballet. But Pangea's greatest irony, even as it reached its peak, the forces that would tear it apart were already at work. Deep beneath the surface, heat from Earth's mantle began to stir, creating weak spots in the supercontinent's foundation. Like a sheet of ice cracking under pressure, Pangea started to fracture along fault lines that would one day become the Atlantic Ocean. The first splits were subtle, a rift valley here, a volcanic eruption there, but over millions of years they grew into yawning chasms, flooding with water and isolating continents like pieces of a broken plate. Life on Pangea faced its own upheaval. With so much land locked together, climates became extreme, vast deserts stretched across the interior, while coastlines experienced brutal seasonal swings. Yet this harsh environment also spurred evolution, pushing species to adapt or perish. Early reptiles, ancestors of dinosaurs and eventually mammals, seized the opportunity, diversifying into niches left open by Pangea's unstable ecosystems. In a way, the supercontinent's dominance set the stage for the age of reptiles, and ultimately our own story. What's truly mind-bending is how recently this all happened in geological terms. 250 million years might sound ancient, but it's just the last 5% of Earth's history. The rocks beneath our feet, the fossils in museum displays, they're all fragments of Pangea's legacy, whispering clues about a world that once was. And if you listen closely, you can still hear the echoes of that ancient collision in the slow creep of continents today, still drifting, still reshaping our planet inch by inch. When two continents meet, it's less like a collision and more like a slow-motion train wreck unfolding over geologic time. Picture two massive slabs of rock, each dozens of miles thick, inching toward each other at about the speed your fingernails grow. There's no sudden impact, just an irresistible force meeting an immovable object with consequences that ripple across millennia. The secret lies in what happens when these continental plates finally touch. Unlike thinner oceanic crust that can dive beneath another plate in a process called subduction, continental crust is like a buoyant cork. It refuses to sink easily into the mantle below. Instead, the edges crumple and fold like a rug pushed against a wall, forcing rock layers upward in dramatic waves. This is how the Himalayas, the Alps, and the Andes were born, not in days or years, but through relentless pressure accumulating over millions of years. But the process isn't smooth or quiet. As continents grind together, the friction generates devastating earthquakes, some so powerful they'd register off the scale of modern seismographs. Meanwhile, the intense pressure melts rock deep below, fueling volcanic eruptions that spew ash and lava across the landscape. Entire regions can be lifted or tilted, diverting rivers, drowning coastlines, or creating vast inland seas. Perhaps the most fascinating aspect is how these collisions leave behind geologic fingerprints. In the Rocky Mountains, you can find marine fossils at towering elevations, proof that these peaks were once submerged seafloor before being thrust skyward. In Scandinavia, the land is still rebounding upward, slowly rising after the weight of ancient glaciers compressed it during the last ice age. And this isn't just ancient history. Right now, Africa's gradual push into Europe is wrinkling up the Mediterranean basin, foreshadowing future mountain ranges yet to form. Australia's northward drift guarantees a collision with Asia that will rewrite maps millions of years from now. The planet we know is just a snapshot in an endless cycle of continental encounters, each collision reshaping Earth's surface in ways we're only beginning to understand. Standing at the foot of Mount Everest today, it's hard to fathom that you're witnessing a crash scene frozen in time, one that's still unfolding with unimaginable slowness. The Himalayas aren't just mountains, they're the crumpled wreckage of a continental collision 50 million years in the making, where India, once a lone island drifting across the ancient Tethys Ocean, slammed into Eurasia with enough force to warp the planet's surface. What makes this collision so extraordinary is India's incredible speed. While most tectonic plates creep along at about the pace your hair grows, an inch or two per year, India raced northward at nearly 6 inches annually, covering over 2,000 miles in just 50 million years. That's geologic highway speeds propelled by massive convection currents deep in Earth's mantle. When this high-speed continent finally hit Asia, it didn't just stop, it plowed forward, bulldozing the ocean floor ahead of it upward like a slow-motion car hood crumpling in a crash. The result, a mountain range so vast it altered global weather patterns. As India pushed under Eurasia, the crust buckled into towering folds, creating not just Everest but the entire Tibetan Plateau, a raised slab of land the size of Western Europe, averaging over 3 miles above sea level. This plateau became Earth's largest elevation change outside the deep ocean trenches, acting like a stone in a stream that diverts jet streams and gives birth to monsoons. But the most startling fact, the collision is far from over. India still moves north at nearly 2 inches per year, about the width of your thumb, every decade, forcing the Himalayas upward by roughly half an inch annually. That growth isn't gentle. It comes in violent jolts through earthquakes as rock layers snap under pressure. The 2015 Nepal quake that killed nearly 9,000 people was just one small adjustment in this ongoing collision, a reminder that the earth beneath us is anything but still. Hidden within these mountains lies another marvel, the remains of the Tethys Ocean itself. High on Everest slopes, climbers find fossilized sea creatures embedded in limestone, proof that these peaks were once seabed. Even now, marine sediments continue to be thrust upward, carried like cargo on India's relentless push northward. Geologists estimate that if the collision continues another 20 million years, the Himalayas could surpass 30,000 feet, taller than any mountain in Earth's history. Yet nothing lasts forever. Erosion claws at these peaks just as tectonic forces build them up, with rivers like the Ganges and Brahmaputra carrying Himalayan rock grain by grain back to the sea. It's a cosmic balancing act, creation and destruction locked in an endless dance, with the Himalayas as their fleeting masterpiece. And somewhere far in the future, when India finally stops moving, erosion will have the last word, slowly wearing these mountains down until only their roots remain, waiting for the next great collision to reshape the world again. The Alps may lack the Himalayan sky-piercing heights, but their story reveals just how deeply continental collisions shape entire regions, not just through mountains, but through climate, waterways, and even the fate of civilizations. Picture Europe 60 million years ago. Africa, adrift on tectonic currents, began its slow-motion nudge northward. The oceanic crust between the continents, an ancient sea called Tethys, was no match for the pressure. Like a sheet of aluminum foil caught in a vise, the seafloor crumpled, then vanished beneath Europe, dragging sediments upward into jagged folds. These weren't just any mountains, they were a geological accordion, compressing layers of limestone, granite, and even marine fossils into the peaks we know today. What sets the Alps apart is time. While the Himalayas are still rising, the Alps have endured 80 million years of erosion. Glaciers carving U-shaped valleys, rivers like the Rhine and Rhone slicing through soft rock, leaving behind the iconic sawtooth ridges. Yet their weathered grandeur hides a surprising truth. These mountains were once taller than the modern Himalayas, the Matterhorn's iconic pyramid, just the stubborn core of a peak whose outer layers have long since washed away. But the Alps' real legacy lies beyond geology. Their formation redirected Europe's entire drainage system, creating the Danube and Po River basins waterways that would become cradles of human settlement. The snowmelt from alpine peaks fed fertile plains where Roman aqueducts and medieval trade routes flourished. Even the region's climate bears their fingerprint. The mountains act as a barrier, trapping Mediterranean warmth to the south while casting a rain shadow that shapes the forests and vineyards of Central Europe. Perhaps most remarkably, the collision isn't over. Africa still pushes north at nearly an inch per year, squeezing the Mediterranean like a watermelon seed. Earthquakes in Italy and Greece hint at the strain. Just last century, a quake near Messina killed over 100,000 as the African plate scraped beneath Sicily. Meanwhile, the Alps themselves, though eroding, still rise slightly as the crust rebounds from ancient Ice Age glaciers. It's a reminder that even finished mountains are works in progress, their stories still being written in the slow ink of tectonic motion. Hidden within alpine rock lies another secret, the ghosts of older collisions. In Switzerland's Gotthard Pass, geologists find stones that once belonged to Africa, chunks of volcanic rock carried north like cargo on a conveyor belt. These outliers, called exotic terrains, are geological hitchhikers, proof that continents don't just collide. They exchange fragments, stitching together pieces of Earth's crust like a patchwork quilt. And here's the twist: the Alps may one day vanish entirely. Given enough time, erosion could reduce them to gentle hills, just as it leveled their ancient predecessors, the Caledonian and Variscan ranges. But new mountains will rise elsewhere, perhaps where Africa's northern march crumples Spain against France, or where Australia's drift reshapes Southeast Asia. The Earth's face is never static, it's a canvas forever being redrawn by the slow, inevitable dance of continents. The Appalachians tell a humbling story of mountains that once touched the sky, now weathered into gentle curves and rolling valleys. Today, their highest peaks barely reach 6,000 feet, mere shadows of their former glory. But travel back 300 million years, and you'd find a landscape that would dwarf even the modern Himalayas, a jagged, towering spine born from one of Earth's most violent continental collisions. This was the climax of Pangea's formation, when North America, a drifting landmass called Laurentia, slammed into the combined bulk of Africa and Europe. The impact was so colossal that it didn't just push rock upward. It shattered entire regions, folding the crust like a rug shoved against a wall. The pressure was unimaginable. Sedimentary layers that had once lain flat on ancient seafloors were flipped vertically, while molten rock surged upward, creating the granite cores that still anchor these mountains today. Hidden within these worn-down peaks are time capsules of that ancient violence. In places like New Hampshire's White Mountains or the Blue Ridge of Virginia, hikers can spot bands of quartzite, a rock so hard it resists erosion, standing like ribs protruding from the earth. These were once the deepest layers of the pre-collision ocean floor, forced upward until they became mountaintops. Even more telling are the coal seams scattered through Appalachia, formed from swampy forests that thrived in the collision's aftermath, only to be buried and compressed as the mountains grew. The Appalachians also hide a secret that connects continents. Along their eastern flank, from Alabama to Newfoundland, runs a zone of shattered rock called the Piedmont. Here, geologists find fragments of volcanic islands and ocean crust debris from an ancient sea that vanished when Africa closed the gap. These exotic rocks, some over 1 billion years old, are like puzzle pieces that perfectly match formations in Morocco and Scotland, proving these now distant lands were once locked together in Pangea's embrace. Time has been both cruel and kind to these mountains. Glaciers during the ice ages carved deep valleys, while relentless rainfall and rivers like the Susquehanna and Tennessee slowly washed away entire peaks grain by grain. But erosion hasn't just destroyed, it's also revealed. The very reason we know so much about the Appalachians' past is because weathering has exposed their inner layers like the pages of a book, allowing scientists to read the story written in their stone. What's truly astonishing is how long this range has endured. While younger mountains like the Rockies still stand tall, the Appalachians have survived nearly 300 million years of punishment, a testament to the sheer force of their creation. They've watched as dinosaurs rose and fell, as mammals took over, and as humans carved roads through their passes. And though they may seem quiet now, they're not done changing. Even today, the crust beneath them slowly rebounds upward, freed from the weight of ancient glaciers, rising at nearly 1 millimeter per year, a silent echo of the titanic forces that built them. Standing in the Appalachians today, you're walking on the roots of a mountain range that once rivaled Everest. Their softened peaks are a reminder that no landscape lasts forever, that even the mightiest geological wonders will one day surrender to time. But they're also proof of Earth's endless creativity, where the rubble of one collision becomes the foundation for the next act in our planet's ever-changing story. Rising like a weathered spine between Europe and Asia, the Ural Mountains tell a story of ancient violence frozen in stone. These worn-down peaks, stretching over 1,500 miles through Russia, were once the fiery frontier where two continents welded themselves together, a collision so old it predates even the dinosaurs. Today, their gentle slopes and forested valleys give little hint of the cataclysm that created them, but the clues are there for those who know where to look. 300 million years ago, the Urals were a towering, jagged range, born when the landmass of Siberia crashed into a collection of smaller continents called Baltica. Picture the force required to squeeze an entire ocean, the Ural Ocean, out of existence. Its seafloor crumpled upward into peaks that may have rivaled the modern Andes. The heat and pressure were so intense that they transformed ordinary rock into treasure troves of minerals, glistening veins of malachite, deep red rubies, and platinum, deposits so rich they fueled Russia's industrial rise. These aren't just pretty rocks, they are chemical snapshots of the extreme conditions that forged them, locked in stone like messages from the deep past. What makes the Urals extraordinary is how they've faded without disappearing. Unlike younger ranges still growing from active collisions, the Urals are geologically retired, their tectonic engines shut down long ago. Erosion has filed them down to their roots, exposing layers that reveal their entire life story. In the southern Urals, you can hike across what was once the heart of the collision zone, a tangle of folded rock where continental slabs rammed together like slow-motion battering rams. Further north, glaciers during the ice ages carved wide valleys, leaving behind isolated peaks that stand like sentinels of a forgotten war. Yet even in their quiet old age, the Urals shape the world around them. They act as a natural barrier, dividing Europe's humid air masses from Asia's drier continental climate. Their mineral wealth built cities like Yekaterinburg, where the Romanov dynasty met its end, and their passes became highways for empires, from Mongol horsemen to Russian railway builders. The very word Ural comes from the Turkic term for belt, a fitting name for this rugged seam that stitches two continents together. Perhaps the most haunting lesson of the Urals is their impermanence. Given enough time, even the mightiest mountains surrender to wind and water. The same forces that leveled older ranges before them are slowly reducing the Urals to rolling hills, a fate that awaits the Himalayas and Alps millions of years from now. But their legacy endures in the very definition of continents. Because of this ancient collision, geographers still debate whether Europe and Asia are truly separate landmasses or just cultural labels on a single, unbroken plate. Standing in the Urals today, you're walking across a fossilized wound in Earth's crust, a place where the planet healed itself by stitching continents together. Their quiet grandeur is a reminder that even the most violent geological dramas fade into stillness, leaving behind only scars and stories written in stone. And somewhere far in the future, when new mountains rise from fresh collisions, they too will whisper tales of their birth to whatever creatures walk their slopes. Long before Pangea stitched together nearly all of Earth's land, another supercontinent dominated the southern hemisphere, Gondwana, a sprawling mass of rock and jungle that held what would become South America, Africa, Antarctica, Australia, and India in its grip. Imagine standing on its shores 500 million years ago. No Atlantic Ocean separating Brazil from Angola, no Indian Ocean dividing Madagascar from India, just an unbroken expanse of forests, deserts, and rivers stretching from pole to pole. This wasn't just a landmass, it was a biological ark carrying species that would evolve in isolation for millions of years after its breakup. The clues to Gondwana's existence are etched into the modern world like a half-erased map. Run your finger along the eastern coast of South America, and you'll notice it slots almost perfectly against Africa's western edge, a fit so precise it's as if someone tore a piece of paper in two. But the proof goes far beyond coastlines. Dig into the rocks of Brazil's Paraná Basin, and you'll find layers of volcanic ash identical to those in Namibia's Etendeka Plateau, evidence of the same eruptions frozen in stone on opposite sides of the Atlantic. Even more telling are the fossils, the tiny, freshwater reptile Mesosaurus, whose remains are found only in South America and southern Africa, or the Glossopteris fern, whose imprints appear like botanical fingerprints across every former piece of Gondwana. When this southern giant began to fracture 180 million years ago, it wasn't a clean break, but a slow, grueling unraveling. Rift valleys, gaping wounds in the crust, split the supercontinent like cracks in drying mud. Magma welled up to fill the gaps, hardening into basalt cliffs that now form the dramatic edges of continents. The first split sent Africa and South America drifting apart, opening the South Atlantic at roughly the speed fingernails grow. Antarctica, still temperate and forested at the time, clung to Australia and South America until the final thread snapped, stranding it in polar isolation. India, meanwhile, broke free entirely, embarking on its solo sprint northward, a journey that would end in the cataclysmic birth of the Himalayas. Gondwana's breakup didn't just rearrange the continents, it rewrote Earth's climate. As landmasses migrated toward the poles, ice sheets expanded, reflecting sunlight back into space and cooling the planet. The opening of the Drake Passage between South America and Antarctica unleashed a circumpolar current that isolated the southern continent, turning it into the frozen desert we know today. Meanwhile, the northward drift of Africa and India closed off ancient seas, triggering shifts in ocean circulation that may have spurred the evolution of modern mammals. Yet Gondwana's legacy isn't just geological, it's written into life itself. The flightless ratite birds, ostriches in Africa, emus in Australia, rhees in South America share a common ancestor that once roamed the supercontinent's forest. Ancient lineages of marsupials, now found mostly in Australia, once thrived across Gondwana before continental drift left them stranded. Even the bizarre, long-lost species of Antarctica, like the tusked mammal Lystrosaurus, tell a story of interconnected ecosystems torn apart by tectonic forces. Today, the echoes of Gondwana are everywhere. When a monsoon drenches India's western Ghats, it's feeding forests that evolved alongside Madagascar's rainforests before the continents parted. When scientists drill into Antarctica's ice, they uncover fossilized tree stumps from a time when the continent was green. And deep beneath the Atlantic, magnetic stripes on the seafloor trace India's frantic northward dash like tire tracks across geologic time. Gondwana may be gone, but its fingerprints linger in the rocks, in the climate, and in the living things that still carry its ancient story forward. Laurasia may not be as famous as its southern sibling Gondwana, but this northern supercontinent played an equally pivotal role in shaping our planet. Picture a vast, interconnected land of towering conifer forests and sprawling floodplains, where the future sites of New York, Moscow, and Beijing all sat within the same continental mass. While Gondwana was assembling the southern pieces of Pangea, Laurasia was busy welding together the north, a process that involved some of Earth's most dramatic collisions long before the age of dinosaurs. The birth of Laurasia began with a series of ancient mergers. Around 300 million years ago, the landmasses that would become North America and Europe, then called Laurentia and Baltica, crashed together in a slow-motion fusion. The impact was so powerful it raised a mountain range called the Caledonians, whose eroded roots now stretch from Norway to the Appalachian foothills. But the real drama came when Siberia, a rogue continental plate, slammed into this growing northern assembly. The force of that collision created the Ural Mountains, effectively stitching Asia to Europe and completing Laurasia's core. What's astonishing is how clearly these events are preserved in the geology beneath our feet. In the Arctic archipelago of Svalbard, coal seams filled with fossilized tropical plants reveal that this frozen wilderness once lay near the equator as part of Laurasia's warm interior. Meanwhile, magnetic signatures in Scottish and Canadian rocks match like puzzle pieces, proving these now distant lands were once neighbors. Even the distinctive red sandstones of the American Southwest have twins in Europe, sedimentary layers deposited in the same vast river systems when the continents were joined. When Pangea finally fractured, Laurasia didn't just split, it unraveled in stages. The first break came as the North Atlantic began to open, peeling Greenland away from Europe and North America like a zipper unfastening. Then, about 55 million years ago, a volcanic surge near Iceland accelerated the separation, flooding the rift with lava that hardened into the basalt cliffs now visible in Ireland's Giant's Causeway and Newfoundland's Tablelands. As the continents drifted, they carried fragments of their shared history. Identical dinosaur fossils found in Alberta and Mongolia testify to Laurasia's former unity, while the distribution of ancient mammal groups like multituberculates traces migration routes that only made sense when the continents were connected. Laurasia's legacy isn't just written in rock, it's etched into Earth's climate. The northward drift of its fragments created the modern Arctic Ocean, a process that triggered ice ages by altering ocean currents. The collision of India with Asia, a plate that was once part of Laurasia, uplifted the Tibetan Plateau and redirected atmospheric circulation, giving rise to the Asian monsoons. Even today, the slow separation of North America and Europe continues at roughly the speed fingernails grow, with earthquakes along the mid-Atlantic ridge marking the ever-widening gap. Perhaps the most poetic evidence of Laurasia lies in life itself. The circumpolar distribution of plants like the Arctic poppy or animals like the brown bear reflects lineages that once roamed freely across the supercontinent before continental drift isolated them. In the DNA of these species, scientists find genetic signatures of ancient connections, biological echoes of a time when the world's northern lands were one. Standing on the shores of the Arctic today, you're looking at the ghost of a supercontinent. The same forces that built Laurasia are still at work, quietly rearranging the planet beneath our feet. And somewhere in the distant future, its fragments may yet reunite, not as Laurasia, but as part of whatever new supercontinent Earth's restless tectonic dance creates next. Between the colossal landmasses of Gondwana and Laurasia, a vanished world once thrived. The Tethys Ocean, a blue expanse so vast it could have swallowed the modern Mediterranean a dozen times over. This wasn't just any ancient sea, it was Earth's original superhighway, a warm, shallow corridor that connected the planet's oceans for nearly 300 million years. Picture turquoise waters stretching from what's now the Caribbean to Southeast Asia, teeming with creatures that would rewrite the story of life on Earth. Yet today, all that remains of this aquatic giant are fragments, a few salty puddles like the Black Sea, limestone cliffs in the Dolomites packed with seashells, and the ghostly outlines of its seafloor crumpled into the peaks of the Himalayas. The Tethys was born from division. As Pangea began to rift apart 200 million years ago, the newborn Atlantic Ocean pushed Europe and Africa northward, squeezing the Tethys between them like a watermelon seed caught between closing fingers. For eons, it endured this slow-motion vise, its waters growing shallower as continental shelves collided, its currents shifting as new land bridges emerged. Marine life flourished in its tropical warmth ammonites with spiral shells like living fractals, early whales no bigger than dolphins, and reefs built by clams so massive they could weigh half a ton. These weren't just inhabitants, they were pioneers, evolving in isolation before spreading worldwide as the Tethys became a biological crossroads. But the ocean's fate was sealed when Africa and India began their relentless march north. As these continents bulldozed into Eurasia, the Tethys had nowhere to go. Its seafloor dense oceanic crust did what all oceanic crust must eventually do. It dove beneath the continents in a process called subduction, dragging entire ecosystems into the mantle. The water itself didn't vanish overnight. It retreated in stages, leaving behind chains of inland seas like the Paratethys, a megalake that once covered much of Eastern Europe and Central Asia. Fossilized shorelines in the Caucasus Mountains reveal how this shrinking sea turned into a brackish wonderland, home to miniature whales and giant ostracods, creatures adapted to an ever-changing world. The closure of the Tethys didn't just erase an ocean, it rewired the planet. When the final connections to the Indian Ocean snapped shut around 15 million years ago, Earth's climate went haywire. Without warm Tethyan currents flowing east-west, new circulation patterns emerged, triggering the Asian monsoons and drying out Africa's once lush interior. The Mediterranean, the Tethys' last gasp, nearly vanished entirely during the Messinian salinity crisis 6 million years ago, when tectonic shifts dammed the Strait of Gibraltar. What was left evaporated into a super salty death valley 2 miles deep, until the Atlantic burst back in with a flood so colossal it would have made Niagara Falls look like a leaky faucet. Yet the Tethys' most enduring legacy lies in the mountains it created. Every time a piece of its seafloor got caught in a continental collision, it was thrust upward, carrying marine fossils to unthinkable heights. In the Austrian Alps, climbers find oyster shells embedded in cliffs 9,000 feet above sea level. The summit of Mount Everest contains limestone formed from the skeletons of plankton that once drifted in Tethyan waters. Even the oil fields of the Middle East owe their existence to this lost ocean. Their black gold is the preserved remains of Tethyan algae, cooked and compressed over eons. Today, the spirit of the Tethys lives on in unexpected ways. When you swim in the Mediterranean, you're floating in its diluted remnants. When monsoons drench India, they're following atmospheric rhythms set by the ocean's closure. And when geologists in Cyprus study a chunk of ancient seafloor called the Troodos ophiolite, they're essentially walking across the Tethys' gravestone, a slab of crust so perfectly preserved it's become a Rosetta Stone for understanding Earth's tectonic machinery. The story of the Tethys is a reminder that nothing on our planet is permanent, not oceans, not continents, not even the tallest mountains. It's a tale written in stone and water, a testament to the forces that keep Earth forever restless, forever new. And somewhere in the geologic future, another ocean may follow in its footsteps, born from the slow, inevitable dance of continents yet to collide. Beneath our feet, Earth is never truly still. It's a planet in perpetual motion, driven by forces so powerful they can shove continents together like bumper cars. The key to understanding these monumental collisions lies in plate tectonics, the grand unifying theory that explains how our planet's outer shell behaves. Imagine Earth's crust not as a single, solid layer, but as a colossal jigsaw puzzle with each piece, some carrying entire continents, others just ocean floor constantly jostling for position atop the seething mantle below. These tectonic plates move at speeds ranging from the sluggish pace of growing fingernails to the brisk clip of hair growth, propelled by convection currents in the mantle that act like a slow-motion conveyor belt. Where two plates carrying continental crust meet, something extraordinary happens. Unlike dense oceanic plates that readily dive beneath one another, continents are stubborn. Their buoyant granite foundations resist subduction. Instead, they crumple and fold in spectacular slow motion, compressing rock layers like an accordion and thrusting up mountain ranges where flat land once lay. The process isn't uniform across the globe. Some collisions, like India's ongoing impact with Asia, are head-on smash-ups that produce towering peaks. Others, like Africa's oblique push into Europe, create complex tangles of mountain chains and twisting fault lines. Even the way plates grind past each other sideways, as along California's San Andreas Fault, can influence collisions elsewhere by changing the overall stress patterns across entire continents. What keeps this planetary engine running? The answer lies deep underground, where radioactive decay and residual heat from Earth's formation keep the mantle churning at temperatures hot enough to melt rock. This thermal energy doesn't just move plates, it recycles them. Oceanic crust born at mid-ocean ridges like the Atlantic's spreading center eventually grows cold and dense, sinking back into the mantle at subduction zones to be melted down and reborn. Continents, however, are the survivors of this cycle, too light to sink, accumulating like foam on the surface of a simmering pot. The evidence for this grand mechanism is everywhere. Magnetic stripes frozen into seafloor basalt reveal the history of oceans spreading like tree rings. Matching rock formations and fossils on opposite sides of oceans testify to continents torn apart. Even something as simple as the distribution of earthquakes and volcanoes follows the edges of plates with uncanny precision, outlining the boundaries of Earth's mobile crust in real time. Yet for all its power, plate tectonics operates on time scales that defy human perception. The Himalayas have risen 8 miles in 50 million years, a blink in geologic terms, but unimaginably slow to our brief lifespans. This disconnect makes tectonic movement hard to grasp until disaster strikes. A magnitude 9 earthquake in Japan, a volcanic eruption in Iceland, or a sudden shift along Turkey's North Anatolian fault. These violent events are reminders that the peaceful stability we take for granted is an illusion. Earth's crust is always adjusting, always moving toward the next great collision or rift. Looking ahead, plate tectonics promises even more dramatic changes. The Atlantic will continue widening as Africa marches north, eventually squeezing the Mediterranean out of existence. Australia's northward drift may one day fuse it with Southeast Asia, while California could detach from North America entirely along the San Andreas Fault. These future rearrangements remind us that the map we know is just a snapshot in an endless film, one where continents dance to the slow, irresistible rhythm of Earth's internal heat. Hidden within ordinary-looking rocks lies one of Earth's most extraordinary archives, not written in words, but in magnetism. When volcanic lava cools or sediments settle during continental collisions, tiny mineral grains within them, like magnetite, act like microscopic compass needles. They align with Earth's magnetic field at that precise moment in geologic time, then freeze in place, preserving a snapshot of the planet's invisible forces. These unassuming stones become time capsules, locking away secrets of where they formed and how the ground beneath them was moving. Think of it like a cosmic fingerprint. Earth's magnetic field isn't static, it flips polarity every few 100,000 years, with north and south poles swapping places. When scientists drill into ancient lava flows or sedimentary layers from collision zones, they uncover bands of rock with opposing magnetic orientations. By matching these patterns across continents, they can trace which landmasses were once connected. For example, identical magnetic stripes in rocks from Brazil and West Africa confirmed their shared past in Gondwana, while anomalies in Himalayan sediments revealed how India twisted as it plowed into Asia. But the real magic happens when this magnetic data meets modern technology. Sophisticated instruments called magnetometers can detect field strengths 1,000,000 times weaker than Earth's current magnetism. In labs, researchers heat samples to unlock their magnetic memories, then reconstruct ancient pole positions. Over decades, these painstaking measurements have revealed startling truths, like how North America gradually rotated counterclockwise as it broke free from Europe, or how Australia once sat much farther south before its northward sprint. Some of the most compelling evidence comes from apparent polar wander paths, curves tracking how Earth's magnetic poles seem to move over time. When separate continents show identical wander paths before diverging, it's proof they were once joined. The Urals, for instance, preserve a magnetic record showing how Siberia's path merged with Europe's after their collision, stitching together Laurasia. Even more remarkably, when researchers recently analyzed 2-billion-year-old rocks from Canada and Australia, their magnetic signatures aligned perfectly, hinting at a supercontinent so ancient it predates even Rodinia. This magnetic detective work doesn't just illuminate the past, it helps predict Earth's future. By understanding how plates moved during earlier collisions, scientists can model where current motions might lead. The Atlantic's widening and the Pacific's slow closure follow patterns written in magnetic stone. Even climate research benefits. Magnetic data from collision zones reveal how mountain uplift altered wind patterns, triggering ice ages or monsoons. Yet for all its precision, paleomagnetism has its mysteries. Some rocks retain multiple magnetic signatures, overwritten by later geologic events like reheating during mountain formation. Others show anomalies that defy explanation, like the bizarre magnetic zones in South Africa's Bushveld complex, a relic of ancient magma flows during Gondwana's assembly. These quirks remind us that Earth's story is complex, written in a language we're still learning to read. The next time you pick up a plain gray rock, consider this. It might hold the key to understanding how continents danced across the globe millions of years before humans walked the Earth. What looks like ordinary stone could be a page from our planet's greatest adventure, a tale of collisions, wanderings, and constant change, all recorded in the quiet persistence of magnetism. Fossils are nature's time capsules, preserving moments from Earth's distant past in stone. When continents collide, they don't just reshape landscapes, they entomb entire ecosystems, locking away clues to lost worlds in layers of rock. Take the humble Glossopteris fern, a plant so unassuming you might overlook it in a fossil display. Yet its delicate imprints, found identically in South America, Africa, India, Australia, and Antarctica, became the smoking gun that proved these lands were once fused together as Gondwana. How else could the same prehistoric plant appear on continents now separated by thousands of miles of ocean? Some of the most compelling fossil evidence comes from creatures that never meant to become globe-trotters. The Cynognathus, a dog-sized reptile that roamed 240 million years ago, left its bones scattered across South Africa and Argentina. Lystrosaurus, a barrel-chested herbivore with tusks, somehow managed to fossilize from Russia to Antarctica. These animals weren't oceanic explorers, they were land dwellers whose habitats were violently ripped apart by continental drift. Their remains are like pieces of a jigsaw puzzle, scattered by tectonic forces, but still fitting together perfectly when scientists reassemble them on maps of ancient supercontinents. But fossils reveal more than just past connections. They show how life adapted to Earth's shifting stage. In the Himalayas, marine fossils sit miles above sea level, telling the story of an ocean floor thrust skyward by India's collision. In the Alps, the shells of tiny sea creatures called nummulites, each no larger than a coin, form entire limestone mountains, proof that shallow Tethys ocean waters once lapped where peaks now tower. Even coal seams, compressed from swamp forests that flourished in Pangea's humid interior, trace how ecosystems migrated as continents moved. Perhaps the most haunting fossil records come from extinction events bookending continental collisions. The end Permian mass extinction, Earth's deadliest, coincided with Pangea's assembly, as volcanic eruptions poisoned skies and collapsing coastlines destroyed habitats. Conversely, the breakup of supercontinents often triggered evolutionary explosions, with isolated landmasses becoming laboratories for new life forms. Australia's marsupials, Madagascar's lemurs, South America's anteaters all evolved distinct forms after their homelands drifted into isolation. Today, paleontologists use cutting-edge tools to read these stone archives in ways early geologists never imagined. CT scans reveal hidden bone structures in fossilized dinosaurs from connected continents, while chemical isotopes in teeth track ancient migration routes across land bridges long vanished. Every discovery adds another stitch to the tapestry of Earth's history, showing how life and land are intertwined in an endless dance. The next time you see a fossil in a museum, look closer. You're not just seeing a relic of the past, but a piece of Earth's grandest story. A story written in rock and bone, telling of worlds that moved, creatures that adapted, and a planet forever remaking itself beneath our feet. When continents collide, they don't just rearrange the map, they rewrite the rules of Earth's climate. Picture a towering mountain range rising where flat plains once stretched. acting like a colossal wall that redirects the very flow of the atmosphere. The Himalayas, born from India's dramatic crash into Asia, didn't just create breathtaking peaks, they fundamentally altered weather patterns across half the planet. As these mountains soared skyward, they disrupted the jet stream, forcing moist air from the Indian Ocean to rise, cool, and dump torrential rains across South Asia. This wasn't just a seasonal shift, it was the birth of the modern monsoon system, a cycle of deluges that now feeds billions of people while also unleashing devastating floods. But mountains don't just create rain, they also manufacture deserts. On the opposite side of the Himalayas lies the Tibetan Plateau, a vast, high-altitude desert where rain clouds rarely reach. This rain shadow effect is repeated worldwide. The Andes cast an arid shadow over Chile's Atacama Desert, the driest place on Earth, while the Sierra Nevada starved Nevada's basins of moisture, leaving behind the stark beauty of Death Valley. These climate divides aren't accidents, they're direct consequences of continental collisions that shoved rocks skyward, partitioning the planet into wet and dry zones like a geological zoning board. Climatic ripples extend far beyond rainfall. When the Isthmus of Panama rose from the sea 3 million years ago, a byproduct of tectonic forces grinding the Americas together, it severed ocean currents between the Atlantic and Pacific. This seemingly small change triggered the ice ages, as redirected currents carried warm water northward, fueling snowstorms that built continental glaciers. Similarly, the uplift of the East African Rift Valley, caused by the slow tearing apart of the African plate, created elevated highlands that cooled the local climate, possibly nudging our early ancestors out of forests and onto the savannas where walking upright became an advantage. Perhaps the most profound climate shifts come from the way collisions recycle carbon. When mountains erode, their minerals wash into the sea, where they react with carbon dioxide to form limestone, effectively scrubbing greenhouse gases from the atmosphere. The rise of the Himalayas coincides with a dramatic global cooling over the past 40 million years, as these fresh rocks accelerated Earth's natural carbon sequestration. Conversely, the volcanic activity that often accompanies collisions like the Deccan Traps eruptions during India's northward sprint can pump enough CO2 into the air to warm the planet catastrophically. It's a delicate balance. The same forces that build cooling mountains can also unleash warming fires. These climate upheavals don't just reshape landscapes, they rewrite the story of life itself. The monsoon's arrival allowed tropical rainforests to flourish in Southeast Asia, creating habitats for orangutans and tigers. The drying of Africa's interior spurred the evolution of drought-resistant grasses, which in turn gave rise to herds of grazing mammals and the lions that hunt them. Even mass extinctions often trace back to collision-related climate shifts. The worst die-off in Earth's history, the Permian-Triassic extinction, unfolded as Pangaea's formation triggered volcanic winters, ocean stagnation, and runaway warming all at once. Today, we're living in the climatic aftermath of ancient collisions. The breadbaskets of Pakistan and India owe their fertility to Himalayan snowmelt, while the oil beneath Arabia's deserts formed when the Tethys Ocean closed, trapping marine life in sun-baked basins. As Africa continues its northward march, the Mediterranean's eventual closure could create a new mountain range that redirects European weather patterns entirely. Climate change isn't just a modern phenomenon, it's been Earth's default setting for billions of years, driven by the slow, irresistible dance of continents that refuse to stand still. The collision of continents isn't just about creation, it carries the power to unravel life itself. While mountain ranges rise and oceans vanish, these planetary scale shifts can trigger ecological catastrophes so profound they reset the course of evolution. Consider the Permian-Triassic extinction 252 million years ago. Earth's most devastating mass die-off, where an estimated 90% of marine species and 70% of terrestrial vertebrates vanished. This wasn't random bad luck, it was the dark shadow of Pangea's birth, a cascade of disasters set in motion by continents welding together. As landmasses merged into the supercontinent, coastlines, those vibrant transition zones where marine life thrives, shrank dramatically. Shallow inland seas drained away, stranding species adapted to those environments. Meanwhile, Pangea's vast interior became a super desert, with temperature swings so extreme they challenged even the hardiest organisms. But the real killer lurked beneath the surface. The collision triggered massive volcanic eruptions in what's now Siberia, where lava flows buried an area the size of Europe under miles of molten rock. These eruptions didn't just scorch the land, they pumped the atmosphere full of carbon dioxide and sulfur dioxide, first acidifying oceans, then warming the planet by perhaps 10 degrees Celsius. Marine chemistry went haywire. Oxygen levels plummeted until even the hardiest bacteria struggled to survive. Yet this apocalyptic scenario reveals a paradox: continental collisions are both destroyers and architects of life's diversity. The same Permian catastrophe that nearly emptied Earth's ecosystems also cleared the stage for new players. In the aftermath, survivors like the humble Lystrosaurus, a pig-sized reptile that proliferated across Gondwana, gave rise to lineages that would eventually include dinosaurs and mammals. Similarly, the Cretaceous-Paleogene extinction 66 million years ago, while caused by an asteroid impact, unfolded against a backdrop of continental rearrangement. The breakup of Pangea, creating isolated landmasses where mammals could diversify without dinosaur competition. Modern science uncovers these connections through subtle clues. In China's Mason rock layers, geologists find a thin band of clay marking the Permian extinction, loaded with molecules from ozone-destroying microbes that flourished in the toxic atmosphere. In South Africa's Karoo Basin, fossilized burrows show how some species adapted to the crisis by going underground. Even today, we see echoes of these events: oxygen-starved, dead zones, in oceans mirroring Pangea's marine collapses, or volcanic CO2 emissions offering a scaled-down version of those ancient climate shocks. What makes these episodes so chilling is their relevance. As continents continue their slow dance, future collisions will undoubtedly trigger new upheavals, perhaps not on Permian scales, but with similar mechanisms. The ongoing closure of the Mediterranean as Africa advances could one day disrupt Atlantic currents just as Panama's rise did. The northward drift of Australia might eventually smother Southeast Asia's coral reefs under mountain-building sediments. Earth's story reminds us that stability is an illusion. The ground beneath us is always moving, always capable of rewriting the rules of life with the slow, inexorable force of colliding continents. When continents collide, they don't just build mountains, they forge treasure. The unimaginable pressures and temperatures generated where land masses meet act like nature's alchemy, transforming ordinary rock into veins of gold, seams of platinum, and glittering diamond pipes. Take the Ural Mountains, that ancient suture between Europe and Asia. Beneath their weathered peaks lie some of the richest mineral deposits on Earth. For centuries, miners have tunneled into these collision-shattered rocks, extracting emeralds the size of walnuts and platinum so pure it flows like liquid silver. The same forces that raised these mountains also concentrated rare elements into ores, a geological lottery that fueled empires from the Tsars of Russia to the Industrial Age. The Andes tell a similar story, where the ongoing crunch between the South American plate and the Nazca plate has created a metallic backbone running the continent's length. Chile's Chuquicamata mine, a gash in the Atacama Desert so vast it's visible from space, produces more copper than any other hole in the ground, a metal essential for everything from ancient tools to modern electronics. Nearby, the silver mines of Potosi once bankrolled the Spanish Empire, their wealth literally minted into coins that circled the globe. These aren't random pockets of riches, they're direct products of subduction, where melting oceanic crust releases mineral-laden fluids that percolate upward, depositing metals in fractures like tree roots absorbing nutrients. Diamonds offer perhaps the most dramatic example of collision zone alchemy. Most gem-quality stones form under insane pressures hundreds of miles down, then hitch rides to the surface aboard volcanic elevators called kimberlite pipes. The Canadian Shields diamond mines like Akoti and Diavik exist because an ancient continental smash-up called the Trans-Hudson Orogeny created just the right conditions to propel these carbon crystals upward. Similarly, South Africa's Kimberley mine, birthplace of the diamond rush, taps into pipes forged during Gondwana's assembly, that sparkling engagement ring. It likely contains atoms that once mingled in Earth's mantle before a continental collision spat them back to the surface. Even common minerals tell extraordinary stories. The marble quarries of Carrara, Italy, source of Michelangelo's David, are metamorphosed limestone from the Tethys ocean floor, baked and compressed when Africa plowed into Europe. China's vast tungsten deposits, critical for everything from light bulbs to smartphones, concentrate where the Yangtze Craton collided with the North China Plate eons ago. These resources aren't just economic windfalls, they're chemical time capsules preserving recipes written in the heat and pressure of continental encounters. The real magic lies in how these treasures form. When plates collide, they don't just shove rock around, they create hydrothermal conveyor belts. Superheated water, rich in dissolved metals, circulates through fractured crust like blood through veins. Gold precipitates out when these fluids hit the right temperature and pressure, often collecting in quartz veins along fault lines. Copper and molybdenum concentrate in porphyry deposits around magma chambers, while rare earth elements follow their own cryptic paths through the geological labyrinth. It's a planetary scale refining process, with collisions acting as the crucible. Modern mining technology lets us peer even deeper into this subterranean treasure map. Satellite spectroscopy identifies mineral signatures from orbit, while seismic imaging reveals hidden ore bodies shaped by ancient collisions. In Sweden, geologists recently discovered Europe's largest rare earth deposit by tracing the scars of a billion-year-old continental smash called the Sveko-Norwegian orogeny. Each find reinforces a startling truth. The ground beneath us is a palimpsest of past collisions, with wealth buried in its bones, yet these gifts come with responsibility. The same Urals that gave Russia mineral riches also hold the radioactive legacy of Soviet mines. The gold that built civilizations has also fueled conflicts and environmental damage. As we tap these collision-born treasures, we're reminded that Earth's violent past powers are present, and that understanding these geological processes helps us extract resources more sustainably. After all, the next great mineral deposit is already forming somewhere deep below, as continents continue their slow, wealth-generating dance. Even today, the ground beneath our feet carries echoes of ancient continental collisions, not just in the shape of mountain ranges, but in the violent tremors that periodically shake these regions. The Himalayas, still rising half an inch each year from India's relentless push into Asia, generate thousands of earthquakes annually, some strong enough to topple entire villages. These aren't random acts of nature, they're the Earth's way of releasing pent-up stress along fault lines forged millions of years ago, like a giant slowly shifting in its sleep. Take Nepal's 2015 earthquake as a sobering example. When a section of the main Himalayan thrust fault suddenly slipped, it unleashed energy equivalent to 20 atomic bombs, killing nearly 9,000 people. Geologists later traced this fault's origins directly to the initial collision 50 million years ago, when India first plowed into Eurasia. The same forces that raised Everest are still at work today, creating a seismic time bomb beneath one of the most densely populated regions on Earth. Europe's Alps tell a similar story. In 2016, a magnitude 6.2 quake struck central Italy, reducing medieval towns to rubble. The culprit, stresses from Africa's ongoing nudge against Europe, which reactivate ancient faults buried beneath picturesque vineyards and ski resorts. Even the Apennines, often overshadowed by their taller alpine cousins, are riddled with cracks from the slow closing of the Tethys Ocean, proving that no collision's aftermath is ever truly over. But why do these zones stay active so long after the initial impact? The answer lies in continental crust stubbornness. Unlike oceanic plates that eventually melt back into the mantle, continents are like scars on Earth's surface. They heal but never fully disappear. Fault networks from old collisions remain weak points in the crust, prone to slipping whenever tectonic stresses change. The New Madrid seismic zone in the American Midwest, for instance, still generates quakes from faults created during Pangaea's formation 300 million years ago, despite being thousands of miles from any current plate boundary. Modern technology reveals these hidden dangers in startling detail. Satellite radar can now detect ground movements as subtle as a millimeter per year, showing how regions like Turkey's North Anatolian Fault, a remnant of Africa's collision with Eurasia, inch closer to failure with each passing day. In Bhutan, scientists mapping subsurface stresses discovered that the Himalayas actually store energy like a spring, releasing it in sporadic, catastrophic jolts rather than smooth motion. For the billions living near these sleeping giants, understanding this legacy isn't academic, it's survival. Japan's sophisticated earthquake preparedness stems from living atop the collision zone where the Pacific Plate dives beneath Eurasia. Chile's strict building codes reflect lessons learned from quakes along the South American Nazca Plate boundary. Even in stable regions like Australia, where ancient collision zones are deeply buried, mining operations now monitor microquakes that hint at lingering tectonic ghosts. The next time news reports a major earthquake in Iran, Greece, or Pakistan, look beyond the immediate tragedy. You're witnessing the final chapters of a story that began when continents first crashed together. These seismic echoes remind us that Earth's history isn't confined to textbooks. It's written in the very ground we build our lives upon, and it's still being written today. When continents collide, the Earth doesn't just buckle upward into mountains, it also unleashes fire from below. The same titanic forces that raise peaks like the Himalayas and the Alps also create some of the planet's most spectacular and dangerous volcanoes. This happens because when dense oceanic plates are forced beneath continental plates in a process called subduction, they don't just disappear, they melt. As the sinking plate descends into the searing heat of the mantle, water trapped in its rocks acts like a flux, lowering the melting point of surrounding material. The result, massive chambers of molten rock that surge upward, seeking any weakness in the crust above. The Andes offer one of the most dramatic examples of this fiery aftermath. Here, the Nazca Plate plunges beneath South America at a rate of about 3 inches per year, roughly the speed your hair grows. This ongoing collision has built not just the longest continental mountain range on Earth, but also the planet's most volcanically active landmass outside the Pacific Ring of Fire. From Chile's Villarrica with its mesmerizing lava lake to Peru's Ubinas, which regularly dusts nearby towns with ash, these peaks are both breathtaking and deadly. Their eruptions aren't just localized disasters, they can alter global climate. When Peru's Huaynaputina exploded in 1600, it pumped so much sulfur dioxide into the atmosphere that Europe experienced a year without summer, with frosts in July and failed harvests leading to famine. Yet the relationship between collisions and volcanoes isn't straightforward. Some of the most catastrophic eruptions in history trace back to continental smash-ups that happened tens of millions of years earlier. India's Deccan Traps, a vast plain of volcanic rock covering an area larger than California, formed as the subcontinent tore through the Tethys Ocean en route to Asia. The lava flows here were so immense they may have contributed to the demise of the dinosaurs by releasing climate-altering gases before the asteroid struck. Similarly, the Columbia River basalts in the American Northwest, which erupted over 16 million years ago, have been linked to stresses in the crust as North America overrode ancient oceanic plates. What makes collision-zone volcanoes particularly unpredictable is their chemistry. Unlike the fluid basalt lavas of Hawaiian volcanoes, which flow smoothly, the magma generated by subduction tends to be thick and sticky, loaded with silica from melted continental crust. This viscous magma traps gases like carbon dioxide and water vapor, building pressure until it explodes with terrifying force. The 1985 eruption of Colombia's Nevado del Ruiz demonstrated this danger tragically. Its pyroclastic flows melted glaciers, sending deadly lahars volcanic mudflows that buried the town of Armero and killed over 20,000 people in minutes. But these fiery mountains also give as much as they take. Volcanic soils from the Andes to the Alps are among the most fertile on Earth, supporting agriculture that feeds millions. The same tectonic forces that build them also concentrate precious metals. Chile's copper mines, which produce a third of the world's supply, exist because mineral-rich fluids rose with magma during the Andes Formation. Even geothermal energy harnessed from volcanic regions like Italy's Campi Flegrei traces its origins back to ancient continental collisions. The next time you see a smoking cone in the distance, remember, you're not just looking at a mountain. You're witnessing the final act of a continental collision that may have begun 100 million years ago, as Earth's restless crust continues to reshape itself in fire and stone. And somewhere beneath your feet, the next great eruption may already be brewing, as the slow dance of continents fuels the planet's eternal geological furnace. The ground beneath us may feel solid and unchanging, but the continents are still in motion, drifting on currents of molten rock at speeds that would carry them across an ocean given enough time. This slow dance isn't just a relic of the past. It's a preview of Earth's next great act. Scientists peering into the distant future see a world where the map we know is utterly transformed, where today's scattered landmasses will one day reunite in a colossal embrace. The Atlantic Ocean, currently widening by an inch each year, will eventually reverse course as its mid-ocean ridge cools and sinks. Africa's northward march will squeeze the Mediterranean shut, while Australia's drift toward Asia may fuse the two continents into a single landmass. The result, a future supercontinent some researchers call Amasia, a land where New York and London could once again become neighbors, separated not by an ocean but by mountains yet to rise. This isn't just speculation, it's geology in action. By tracing current plate movements and studying ancient supercontinent cycles, researchers predict Amasia will form in roughly 250 million years, when the Pacific Ocean closes like a zipper and the Americas collide with Asia. Some models suggest it will straddle the North Pole, a frozen titan surrounded by a vast global ocean. Others propose it will form along the equator, where the remnants of Africa, Eurasia, and the Americas crunch together in a slow-motion pileup. These scenarios aren't just academic exercises, they're glimpses of a planetary future where today's coastal cities could become fossilized relics buried deep inland, their former oceanfront views replaced by endless plains or towering peaks. The forces driving this reunion are the same ones that built and destroyed supercontinents before. Earth's mantle convection, that slow churn of heated rock beneath the crust, acts like a planetary conveyor belt, pulling continents apart only to drag them back together over hundreds of millions of years. The Pacific's eventual closure mirrors the fate of the ancient Tethys Ocean, while the Atlantic's predicted reversal echoes how the Iapetus Ocean vanished when continents merged to form Pangea. Even the crust itself carries genetic memory. Old collision zones like the Appalachians and Urals, though worn low by erosion, remain weak points where future continents may realign. What will life be like on this future supercontinent? Climate models paint a stark picture. With so much land concentrated in one area, vast interior deserts could rival the dryness of Pangea's ancient heart. Monsoons might drench newly formed coastlines, while the absence of large oceans to moderate temperatures could trigger extreme seasonal swings. Yet these harsh conditions could also spur evolutionary leaps, just as they did when reptiles diversified on Pangea. Future species descendants of today's mammals, birds, or perhaps entirely new lineages may find themselves adapting to landscapes we can barely imagine, shaped by mountain-building events still millions of years away. The most fascinating aspect isn't just that continents will collide again, it's that this cycle has no end. A major, like all supercontinents before it, will eventually fracture under the same forces that created it, torn apart by upwellings of molten rock that birth new oceans. The planet we call home is a work in progress, its surface endlessly rearranged by tectonic forces that care nothing for human timescales. Our cities, our borders, even our tallest mountains are fleeting features on a canvas that's always being redrawn. When a major forms, Earth won't be reaching a destination. It will simply be writing another chapter in a story that began 4.5 billion years ago and has no final page. Mars stands frozen in time, a geological museum where the exhibits haven't changed for billions of years. While Earth's continents waltz across the globe in an endless tectonic dance, Mars' crust lies still, a single, unbroken shell with no moving plates, no colliding landmasses, no mountain-building collisions. The contrast couldn't be starker. Where our planet constantly reinvents itself through continental smash-ups like India plowing into Asia, Mars' most dramatic features Olympus Mons, Valles Marineris are relics of ancient catastrophes, untouched by the slow-motion remodeling that shapes Earth. This difference isn't just academic, it's the key to understanding why one planet teems with life while the other lies barren. Earth's restlessness comes from its internal heat engine. Radioactive elements decaying in the core, combined with residual warmth from planetary formation, keep the mantle churning like a pot of near-boiling soup. This convection drives plate tectonics, pulling continents apart in some places while shoving them together in others. Mars, though, is too small to retain that fiery momentum. With only half Earth's diameter and just 10% of its mass, the red planet lost its internal heat rapidly, its mantle solidifying like a cooling pot of wax. Without this energy to power the conveyor belt of plate tectonics, Mars' crust became a stagnant lid, its volcanoes erupting in the same spots for eons until they built Olympus Mons, a shield volcano 3 times taller than Everest, yet oddly flat because lava kept piling up in one stationary location rather than spreading along moving plates. The consequences of this geological stagnation ripple across Mars' entire landscape. Earth's active crust recycles carbon through subduction zones and volcanic outgassing, maintaining an atmosphere that regulates temperature and nurtures life. Mars, lacking this cycle, saw its once thick atmosphere bleed away into space, leaving the surface freeze-dried and exposed to lethal radiation. Water that might have pooled in Martian oceans instead either evaporated or retreated underground, leaving behind only dry riverbeds and mineral signatures as clues to a wetter past. Even the planet's famous red color tells a story of geological inactivity. Earth's iron rusts too, but our active water cycle and plate tectonics constantly bury and renew surface materials, while Mars' oxidized dust simply accumulates, painting the entire world in shades of rust. Yet Mars wasn't always this way. Satellite images reveal features that hint at a brief period of tectonic activity early in its history. Vast canyon systems that resemble stretched crust, magnetic stripes in ancient rocks suggesting moving plates, even possible subduction zones frozen in time. Some scientists believe Mars may have experienced a short-lived version of plate tectonics before its small size doomed it to geological hibernation. This makes the planet a tantalizing control experiment. Two rocky worlds formed from similar materials at roughly the same time, but only one developed the sustained dynamism needed to recycle atmospheres, regulate climate, and provide the stable yet evolving environments where life could take hold and thrive. The lesson written across Mars' dusty surface is humbling. Earth's continental collisions aren't just scenic backdrops, they're vital components of a planetary life support system. When the Himalayas rise, they expose fresh rock that absorbs carbon dioxide, helping stabilize the climate. When undersea plates subduct, they recycle minerals essential for life back into the biosphere. Even earthquakes and volcanoes, for all their destructive power, are symptoms of a planet vigorous enough to maintain oceans and atmospheres over billions of years. Mars shows us the alternative, a world where geological stillness leads to environmental stagnation, where the absence of continental drift means the absence of renewal, and where the silence beneath the surface speaks louder than any eruption about why Earth remains, as far as we know, uniquely alive in the solar system. Water might seem like a passive player in Earth's grand geological drama, just filling the oceans and carving valleys over time. But beneath the surface, it's a master manipulator of continental collisions, acting as both lubricant and wrecking ball in the planet's tectonic machinery. When oceanic plates begin their descent into subduction zones, it's not just rock sliding beneath rock. It's waterlogged rock carrying the equivalent of entire seas down into the mantle. This hidden moisture changes everything. Take the Marianas Trench, where the Pacific Plate dives beneath the Philippine Sea Plate. The sediment being dragged down isn't dry, it's saturated with water, both chemically bound in minerals and trapped in pore spaces. As the plate sinks deeper, heat and pressure squeeze this water out like juice from a sponge, but instead of dissipating, it rises into the overlying mantle wedge, triggering a remarkable transformation. The injected water lowers the melting point of mantle rock by hundreds of degrees, creating the magma that fuels volcanic arcs like Japan and the Andes. Without this hydration process, many of Earth's most iconic mountain ranges might never have risen from the sea. Water's influence goes far beyond magma generation. On a microscopic level, it weakens rock crystals through a process called hydrolytic weakening. In subduction zones where rocks endure incredible stresses, even trace amounts of water can make minerals like olivine, normally rigid, behave like stiff putty. This allows plates to bend and slide with less resistance, preventing the entire system from locking up. The difference is staggering. Dry subduction zones produce frequent, devastating earthquakes as plates stick and then violently rupture, while well-lubricated zones tend to creep steadily with fewer catastrophic quakes. The oceans themselves act as geological ballast. Their immense weight depresses seafloor crust, helping to initiate subduction where plates meet. When young, buoyant oceanic crust resists sinking, as seen with the stubborn Nazca Ridge pushing against South America, it's often the accumulating sediments and water pressure that eventually tip the balance. Even the chemistry of seawater plays a role. Chloride ions from saltwater percolating through mid-ocean ridges alter the composition of new crust, making it more prone to bending when its time comes to subduct. Perhaps the most startling evidence of water's importance comes from considering its absence. Venus, Earth's sister planet, shows what happens when a world loses its surface water. While Venus likely had oceans early in its history, a runaway greenhouse effect boiled them away. Today, its crust appears stagnant, no plate tectonics, just occasional catastrophic resurfacing by massive volcanic outbursts. Without water to lubricate subduction and weaken rocks, Venus' lithosphere became too rigid to break into moving plates. Mars tells a similar story of geological stagnation following water loss. Earth's abundant water isn't just a habitat for life, it's the grease that keeps the planetary engine running. This liquid accomplishes feats that defy intuition. In the depths of collision zones, supercritical water, neither liquid nor gas, dissolves silica from surrounding rocks and transports it upward, forming the quartz veins that glitter in mountain ranges worldwide. At even greater pressures, water facilitates the formation of exotic minerals like ringwoodite, which can hold oceans' worth of water within Earth's mantle transition zone. Some scientists speculate that this hidden reservoir contains several times more water than all surface oceans combined, a subterranean sponge that may regulate plate tectonics over geologic time. The next time you stand on a beach, consider this. The waves lapping at your feet aren't just shaping coastlines, they're part of a planetary cooling system. As oceanic plates carry water into the mantle and volcanoes return it to the atmosphere, Earth maintains a delicate hydrogeochemical cycle that has persisted for billions of years. Our planet's unique dance of colliding continents owes as much to its abundant water as to its fiery core. Without these intertwined systems, the ground beneath us might have frozen in place eons ago, leaving Earth as geologically lifeless as its celestial neighbors. Human civilizations didn't just spring up randomly across the globe, they grew where the Earth itself provided the perfect recipe for prosperity. Look at any map of ancient empires, and you'll spot a striking pattern. From the riverbanks of the Indus Valley to the terraced slopes of the Andes, humanity's greatest early achievements blossomed along the scar lines of continental collisions. These zones offered gifts no other landscapes could match: soil so rich it could feed millions, minerals precious enough to build kingdoms, and defensive terrain that protected cities for centuries. The Indus Valley civilization, one of humanity's first urban experiments, thrived on sediments washed down from the growing Himalayas. Every monsoon season, floodwaters carried mineral-rich silt from the young, eroding mountains, depositing it across the plains in layers of fertile black earth. This wasn't just dirt, it was geological alchemy, the powdered remains of an ocean floor that had been thrust skyward, then weathered into the perfect medium for wheat and barley. The same collision that raised the Himalayas also created the Thar Desert as a rain shadow, funneling water into the Indus River system and creating an agricultural heartland larger than ancient Egypt and Mesopotamia combined. Halfway across the world, the Andes presented a different kind of collision bounty. When the Nazca Plate plunged beneath South America, it didn't just build mountains, it forged veins of gold, silver, and copper that would fuel the Inca Empire and later Spanish conquistadors. The terraced farms of Machu Picchu cling to slopes created by tectonic uplift, their microclimates ranging from tropical valleys to alpine pastures within miles. Even the potatoes that became a global staple evolved in this geologically dynamic landscape. their diversity shaped by the elevation changes wrought by continental collision. Mediterranean civilizations tell a similar story. The olive groves of Greece and the vineyards of Italy grow in soils enriched by the same tectonic crunch that raised the Alps and Apennines. When Africa pushed against Europe, it didn't just create stunning landscapes, it exposed marble quarries that gave us Michelangelo's David and the Parthenon, while volcanic activity from the collision zone deposited the obsidian that early traders carried across continents. The very concept of Western civilization emerged from this geologically active cradle. These collision zones offered more than just resources, they shaped human imagination. Himalayan peaks became the abodes of gods in Hindu and Buddhist traditions. The Andes' sawtooth ridges formed the backbone of Inca cosmology, their alignment with solstice sunrises carefully calculated in stone. Even our modern borders often follow ancient geological boundaries. The Indus River remains a political divider, while the Alps have defined European territories for millennia. Today, we still cluster along these ancient collision lines, though we've forgotten their origins. Mexico City sprawls across the remains of an ancient lake basin created by subduction zone volcanism. Tokyo perches precariously where three tectonic plates meet. The lessons are clear: civilization doesn't just adapt to geology, it's fundamentally built upon it, drawing sustenance from lands shaped by forces that began moving long before humans walked the earth. Our greatest cities stand as living monuments to continental collisions that occurred millions of years ago, their foundations literally rooted in the planet's restless geological past. Modern technology has transformed geology from a science of hammers and hand lenses into something resembling a planetary time machine. High above our heads, satellites like the European Space Agency's GOES mission map Earth's gravity field with such precision they can detect ancient subduction zones hidden beneath continents, ghostly scars from collisions that happened hundreds of millions of years ago. These orbital sentinels measure variations in gravitational pull so subtle they reveal where dense oceanic crust was shoved beneath lighter continental plates, creating invisible seams in the planet's foundation. Beneath our feet, seismic tomography, akin to a CT scan for Earth, uses earthquake waves to reconstruct 3D images of the mantle. When researchers analyzed data from thousands of seismic stations, they discovered colossal slabs of ocean floor that sank into the mantle when the Tethys Ocean closed, now lying frozen in the deep like shipwrecks at the bottom of geological time. Some of these remnants dive nearly 2,000 miles downward, their cold, dense material still influencing convection currents that drive modern plate movements. Supercomputers stitch these clues together, running simulations that rewind tectonic history frame by frame. One groundbreaking model from the University of Sydney recreated Pangea's breakup with such accuracy it predicted previously unknown microcontinents, later confirmed by ocean drilling projects. These virtual recreations show continents not as rigid blocks but as malleable masses that stretch and warp during collisions, solving mysteries like why India compressed by nearly 600 miles as it plowed into Asia. The most startling revelations come from combining technologies. Magnetic anomaly data from satellites, when overlaid with seismic images, recently exposed Zealandia, a submerged continent east of Australia that broke from Gondwana 80 million years ago. Meanwhile, LiDAR scans of mountain ranges like the Alps reveal fault networks so complex they resemble shattered glass, explaining why some regions experience earthquakes far from current plate boundaries. These tools don't just illuminate the past, they're rewriting it. Traditional geologic maps showed the Appalachians as a simple chain, but ground-penetrating radar uncovered multiple collision events stacked like pages in a book. Similarly, isotopic analysis of zircon crystals, nature's most durable time capsules, proved parts of Australia once belonged to North America, forcing a complete redraw of Rodinia's proposed configuration. What emerges is a planet far more dynamic than we ever imagined, where continents don't just drift, they dance, fracture, and sometimes vanish entirely beneath their neighbors. And with machine learning now analyzing planetary-scale datasets, we're on the verge of predicting not just where plates have been, but where they're going next, a future where geology becomes as much about prophecy as it is about history. One of the most persistent myths about continental drift is that it happens in a straight line, as if continents glide across the planet's surface like chess pieces on a board. The reality is far messier. Picture a bumper car moving through a crowded arena, bumping, spinning, and sometimes getting stuck for millions of years before lurching forward again. India's journey to Asia wasn't some smooth cruise. It involved twists, rotations, and even a surprising speed boost around 70 million years ago, when mantle currents beneath it suddenly accelerated its northward sprint. Another common misunderstanding is that collisions happen in a single, dramatic moment. In truth, they're more like a slow-motion car crash where the vehicles remain crumpled together for eons. When Africa began nudging into Europe 30 million years ago, it didn't just create the Alps overnight. The collision started with shallow seas flooding the area, followed by sporadic uplifts, volcanic outbursts, and earthquakes that continue to this day. Even now, the Mediterranean is still being squeezed like a wet sponge, with its southern shore rising while the northern edge fractures into a mosaic of microplates. Then there's the idea that all mountain ranges form the same way. While the Himalayas resulted from a head-on collision, the Andes tell a different story, a continental plate overriding an oceanic one, creating volcanoes instead of folded peaks. And some mountains, like Alaska's Denali, are actually remnants of ancient island chains that got welded onto continents like stickers on a suitcase. Perhaps the most dangerous myth is that we've got it all figured out. Just 50 years ago, geologists dismissed the idea that continents could move at all. Today, we're still uncovering surprises like how North America's western edge is a Frankenstein's monster of terrains, chunks of crust that drifted from across the Pacific and stuck like geological postage stamps. Or how Zealandia, a mostly submerged continent the size of India, went unnoticed until satellite gravity maps revealed its outline in 2017. The deeper we dig, the clearer it becomes. Earth's tectonic story isn't some neat textbook diagram, it's a sprawling, chaotic epic where continents jostle, spin, and sometimes even crack apart under their own weight. And every new discovery reminds us that the ground beneath our feet is anything but predictable. From the Himalayas' sky-piercing peaks to the vanished supercontinents that once ruled our planet, Earth's story is written in the slow, unstoppable language of colliding landmasses. These aren't just geological events, they're planetary turning points that forged the very stage upon which life evolved. When India plowed into Asia, it didn't merely create mountains, it rewired global weather patterns, giving birth to monsoons that would feed civilizations. The assembly of Pangea didn't just connect land, it triggered extinctions and evolutionary explosions that ultimately led to the age of dinosaurs and later mammals. Every cliff face, every coal deposit, even the very air we breathe carries echoes of these ancient crashes. But what's truly astonishing is how alive this process remains. Right now, Africa's gradual push into Europe is raising the Alps millimeter by millimeter, while Australia's northward sprint guarantees a future collision with Southeast Asia. The Atlantic widens at the pace your fingernails grow, and the Pacific shrinks by the same relentless logic. We're living on a planet where the ground beneath our cities is in motion, where familiar maps are temporary sketches in Earth's ongoing masterpiece. The same forces that built the Urals 300 million years ago are still shaping tomorrow's mountain ranges. They're just working on time scales that dwarf human history. This grand tectonic dance doesn't just belong to geologists, it's our shared inheritance. When farmers in the Ganges Plain harvest crops nourished by Himalayan minerals, when miners extract Andean copper for our smartphones, even when earthquakes remind us of the planet's restless energy, we're engaging with the consequences of continental collisions. The rocks beneath us are archives waiting to be read, holding clues about everything from climate change to the locations of critical minerals needed for renewable energy. Understanding these processes isn't just about the past, it's about anticipating the challenges and opportunities of our planet's future. So the next time you unfold a map or gaze at distant mountains, remember, you're looking at a snapshot in an epic film that's still playing. The continents will continue their slow waltz long after we're gone, crashing together in new configurations, building future Himalayas and closing oceans yet to form. Our human stories are but brief flickers in this planetary saga, yet through science, we've learned to read Earth's autobiography written in stone. If you've enjoyed this journey through deep time, be sure to like and subscribe for more explorations of our incredible planet. Drop a comment below. We'd love to hear which continental collision fascinates you most. After all, the next great crash could already be underway beneath our feet, setting the stage for Earth's next great